All right, I'm recording now. Okay, here we are. Zebras. I'm gonna try to zoom in on the zebra. I can't. See? Like I don't want to go. I don't want to. I'm afraid to go away from this because more people are going to join. All right. Yeah. Sorry about. I don't know, the whole storm thing. It's not my fault, but I'm just saying, like, we're kind of unsure. Look, we're just going through. We're no matter what, we're just going to take our test and we're going to plug through. Even if I can't talk to you at all, then I'm going to make videos and we're going to keep going. Otherwise, I mean, who knows? So, you know, I'll go into the classroom every time I'm allowed, but who knows, right? Anything happens and they're going to tell us to teach from home. So, and again, just to remind you, if I'm teaching in the class, you're encouraged even to stay home, and because I'm going to be streaming it. However, I'm just saying this one more time. For some of you that are very nervous about being like doing this by computer, and you want to be in class, you're encouraged to come to class. So I'm hoping that only about 8 people or 6 people will want to come to class, and then it'll be a small class. All right. So you guys can hear me okay. All right, back to zebras. No, not zebras. Let's start all the way at the bottom and work our way up to zebras, because that should be our goal. So that's why we're talking about atoms very quickly, because that's to really understand biology, you have to understand chemistry. You have to have not the whole chemistry, right? We're not going to balance equations or do any of that math shit in here. No. So I don't know how to do it. I took my Chem 1 and I got a B, and then I dumped all that information from my head. Don't dump information from your head if you are a science major, right? Keep all this stuff in your head. So anyway, it all starts with atoms. We're going to start putting atoms together to make molecules. So you need to know how atoms interact with each other. Shit, I'm going to turn my AC off. Hold on. Let's see how long I can do that without an AC. Oh, that's so much better for me. You're going to see me start sweating though. Yeah, so we put the atoms together, and there's 4 atoms that we care about in this class. And if you watch the video, you know what they are. Hydrogen. There you go. Hydrogen, oxygen, nitrogen, and our star of the 4, the team leader, carbon. Right? So carbon, hydrogen, nitrogen, oxygen. An easy way to remember that, COHN, Secretary William Cohen under the Clinton administration. All right. Yeah, so 4 atoms that we really concentrate on in this class in biology are those 4 that I mentioned. Those 4 atoms, carbon, hydrogen, nitrogen, oxygen, make about 96% of everything that's living. So remember that number. About 96% of everything living is made from those 4 atoms. And right, so we're biology, we only really care about things that are living. So those 4 atoms are going to be put together starting maybe next week to make 4 molecules that are principally in something living. Carbohydrates, and you don't have to write this down yet. Carbohydrates, lipids, proteins, and nucleic acids. We're going to talk about that. There's a whole chapter about that. So don't worry about that now. But we have 4 atoms, and they're going to make 4 molecules. And then once we got the molecules down, we start putting those together, and we make cells. And then you get groups of cells that perform a common function, and that's a tissue. So my skin is a tissue. It's a group of cells. It's a group of epithelial cells, like these special cells, that are coming together to protect me or whatever it's doing, right? And then you take a bunch of tissues, you put them together, that makes organs. Take a bunch of organs, put it together, that makes an organism, aka zebra. So that's that slide. Oh, I should probably do it this way. All right, so this is just, I'm not going to test you on this. The only thing that I do want you to know for any test is that I want you to know these first 4, most of our body is made from these first 4. Like I was saying, 96%, right? These are other, and there's way more elements than this in our body, right? But if you look at the other ones, calcium, phosphorus, potassium, those are minerals or electrolytes, and don't worry about that for now. Just the first 4. Why is this on? I don't know. Now that I'm looking at it. Okay, because I want to show you what to ignore for right now. Because if you remember from high school chemistry or in your book, they're talking about the s orbital and the p orbital. Forget it. If you don't know it, forget it. I'm not going to ask you about it. You're not going to see these. These ones on the bottom, that's how I do it. I got to let someone in. So you look at that one on the bottom. And then back to class. So these down here. And so an atom, how I envision it, how I always think of it, is a planet. An atom's a planet, and it's got moons going around it. And so you can see the purple. The purple is the planet, and then these 2 right there are 2 moons, and then this line right here is like the orbit. It's just saying that they're orbiting around, right? So that's it, right? And if you remember from the video, you go to the next one. This layout here. So inside the planet, the nucleus of the atom, inside the atom are 2 subatomic particles, 2 things: protons, neutrons. Pro for positive, so it's positively charged. Protons are positively charged. Neutrons, neutral. They don't have a charge, hence the name neutron. The moon that goes around it are called electrons. Those are negatively charged. So don't mess that part up and say that electrons are positive, right? Electrons are negative. So look up here at hydrogen. Inside that purplish area, purple-gray area, there is 1 proton. That's positive. It's not labeled here, you can't see it, but it's 1 proton. And then going around is 1 electron. So 1 positive inside, 1 negative going around. They cancel each other out. So 1 positive, 1 negative. I gotta shut my email off. And then, so it kind of goes like this. The first thing we start with an atom, our first question is how many protons are in that nucleus. So in that purple-gray area, the planet, how many protons? That is the first question, and that's really the only thing we care about. How many protons are in it? And so look at this, I'm skipping ahead a little bit, but look at this periodic table. This one, shit, what can't make it bigger. There you go. So if you look here, you see two numbers on all these things, right? And this is already telling you. You see atomic number and you see atomic mass. So the atomic number is how you define an atom, and that the atomic number is the number of protons. That's it. It's not, has nothing to do with neutrons. It has nothing to do with electrons. We use protons to decide what we're going to call an atom. How do I know to call this atom hydrogen? Why don't I call this atom lithium? Because hydrogen only has one proton. Lithium has, you can see the number in the upper left, 3 protons. Beryllium, 4 protons. Again, you don't need to know all these. You need to know 4. So hydrogen's one of those that you need to know. So hydrogen has just 1 proton in it. Atomic number of 1. Then the other thing you see, the other number, which we're not going to really look at the mass, but it's like the mass or the weight. And to figure out the weight of an atom, we just take the protons and the neutrons, we add them together. That's the weight. So usually you're going to see these numbers are like double, right? 3, 6, roughly, right? We're in biology. We're not doing it exact. 6, 12, something like that, right? So the atomic number 6 of carbon, for example, that's another one you need to know. So atomic number 6, that means there's 6 protons. We're going to assume that if there's 6 protons, there's also 6 neutrons. Sorry. Dude, I'm switching out my air conditioner in the attic, so it's like insulation's all over the house. So carbon, for example, carbon has an atomic number of 6. That means there's 6 protons. We're going to assume that there's 6 neutrons, and we're going to assume that there are 6 electrons. So if there's 6 protons, we assume that there's the same amount of neutrons, same amount of electrons. But it doesn't matter, even if there were more or less, it doesn't matter as long as there's 6 protons, because that's the atomic number. But, you know, if there's 6 protons, then we're going to assume that there's 6 neutrons. So we take those, add them together, 6 plus 6, 6, and that gets us 12, right? And so this whole periodic table is, it's by atomic mass, right? As you go down lower, it gets heavier, right? There's more, or it's actually by atomic number, right? So 1, and then the helium's 2, and then it just keeps going, right? So there's 4 we need to know. Hydrogen, which is 1, and then the other 3 are right next to each other. 6, 7, and 8. Carbon, nitrogen, oxygen. I want you to know the atomic numbers of those 4. And the weight is just double the number, right? The atomic mass of the atomic weight is just double the number. So, and then here it is again. That's kind of like a different look, right? So what they're not showing you, and what I kind of show you in some of the videos, is that there's protons and neutrons on the inside. They're just showing you the electrons. So you're making assumptions here. You're assuming that because there's 1 electron going around, there's 1 proton in the middle. Or carbon, there's 6 electrons going around. That must mean that there's 6 protons and 6 neutrons in the middle, because they all match up. And you might be asking yourself, well, how do I know when they don't match up? You'll know, like the book or whatever you're reading, it'll say to you. For example, you know, how do I know that nitrogen is not, how do I know that the electrons and the protons match up? Well, if they didn't match up, you'd see like a plus or a negative next to it. And we'll get into that. So there's different orbit layers. And so you might have learned something different in chemistry, but I'm just getting you from point A to point B. So what I'm saying to you is not like always true, but for this class, we're going to call it true. The first orbit or shell. So sometimes this thing's called an orbit, and sometimes it's called a shell. It can hold a maximum of 2 electrons. See, so this one has 2. This one has 1 in it. This one has 2. I cannot put a 3rd electron on here. I have to make a new shell to put the 3rd electron on. And then the second shell, that I made, that can hold up to 8. And the 3rd shell holds up to 8. So first shell's 2, second and third shells are 8. We talked about this already. The atomic number being the number of protons in the nucleus. As long as those don't change, we call it carbon. For example, carbon's 6 protons. Once I put 7 protons in there, or that doesn't really happen, but let's say I did that, it's no longer carbon. But if I had 7 neutrons, then it's still carbon. Or if it only had 2 electrons, whatever, it's still carbon. As long as the protons are 6, it's carbon. Atomic weight, add the protons and the neutrons, we call that Dalton. Right, so in the case of carbon, it's 6, the atomic number, and the weight is 12 Daltons. You saw in the periodic table that it was not 12, it was 12.01, whatever. It's not chemistry. We're just doubling it, and we're just going to go with that. An isotope. So that's when you have more neutrons than protons. All right, so if we take carbon, carbon has an atomic number of 6, meaning 6 protons. The atomic mass, we're going to round it, is 12. So that means that there's 6 protons and 6 neutrons. Right? Sometimes you can get some carbons out there in the world floating around have 7 neutrons. So in that case, instead of this being 12, we would say 13, right? Because it's got like 6 protons, but it doesn't have 6 neutrons, it's got 7. So what does that do? What does that do when you put extra? Nothing. I mean, not for us. It changes the, it doesn't change the charge, right? Because neutrons have no charge. So it doesn't matter how many neutrons we put in there. The charge is the same. But at some point, these atoms, it gets way too crowded in that planet, in that nucleus, right? If you keep shoving neutrons in there, it gets too crowded, and that thing's going to break open. And then all the protons and neutrons are going to leak out of it. And depending on what atom, whatever, I don't know what they are. I know carbon, but carbon can hold an extra neutron. It can hold even 2 extra neutrons, but then it starts getting way too crowded. And if you try to stick like 9 in there, like 6 protons and 9 neutrons, it's too much. That thing, the whole thing breaks open, right? So it's radioactive. So I don't know. That's just know that. Just know that isotopes, when you have more protons and neutrons, except the opposite of what I said. When you have more neutrons than protons, that's an isotope. And at some point, you don't need to know what the point is because every atom is different. At some point, it's radioactive. It's like too much, and it breaks open and it leaks all the protons and neutrons everywhere. We use it that's what nuclear medicine is, right? So we can use it. You could take iodine, radioactive iodine, and give it to someone, and it's going to stick to the thyroid gland, and the radioactive iodine starts breaking open and leaking energy all over the thyroid gland. It's not going to give you cancer, but it's going to make like a 3D image of your thyroid gland. So it's a nice way to look at it without slicing your neck open. Or you could do it like in the GI tract. You could take like a barium swallow, and it coats your whole esophagus and stomach, and all those radioactive atoms are breaking and leaking out the protons and the neutrons. Anyway, so we're following this pattern. As you go from left to right and from top to bottom, we're just adding a proton. Lithium has 3 protons, beryllium 4. We don't really care about these. Boron has 5, whatever, we don't care about boron. We do care about carbon. Carbon has 6 protons, nitrogen 7 protons, oxygen 8 protons. And because of that, for now, we're assuming that it has also 8 electrons going around it. And then once you fill your shell, so you notice that this first shell, let's look at carbon. The first shell has 2. The second shell has 4. So that's 6 total, right? And this second shell can hold up to 8. So here, if you look at nitrogen, it's got on its outer shell 5. I had to count it. It took me a second to count it too. I couldn't just look at it and say 5. Even though I've been saying the same thing for like 20 years, I still had to look at it and count it. Oxygen 6, whatever this is, fluorine 7, neon 8. Right now 8, that's it, it's too much. So this has 10 protons right in the middle where I'm pointing, 10 neutrons right in the middle where I'm pointing, and then if you count all the electrons, it's 10. 2 on the first orbit, and then that's it. You got to make a second orbit. 8 on the second. Now that's all that the second can hold is 8. So if you look down here at sodium, that has 11. 11 electrons. You got to make like a new, right? You got to make your third orbit out there. So this outer orbit is the important part. Atoms are very superficial. They're very shallow. Atoms, they don't give a shit about what's inside, about what's in here, about who you are. They just care about the outside. So they would have been very happy last night. So, political joke, sorry. So they only care about the outside. They're very superficial. That's one thing about atoms. It's like a show on Bravo, right, or TLC. The other thing is there's a lot of drama with atoms. They're always getting together, hooking up, but then breaking up. Sometimes bringing in a third atom because they just like to roll that way sometimes. And then they'll bring like in a third atom, and then this one gets jealous and leaves, and like he forgets something and he comes back and like tries to get his wallet, but this atom won't give it to him. You'll see how this all plays out. So that's it's about as interesting as I can make it. But they form a lot of bonds and they break a lot of bonds, and they only care about the outside. They only care about that outer shell. That's all they care. Oh, and to show you, to talk about another way that atoms are superficial, since they only care about the outside, they always want to like fill up that outside shell, right? That outside shell here. And by outside, we call it valence. So anything, the most outer shell or the most outer orbit, we call valence. They always want to get 8, right? They can't get it. Like, look at carbon. Carbon can't have 8 because it only has 6 protons in the middle. So there's 6 electrons on the outside. It's only got 4 here on its outer shell, but it wants 8. It believes in itself. So carbon really wants to get everything that it can. All these atoms want to get everything they can. They all want to be like neon. See, neon's fine. Neon's chill because neon's got all its 8 electrons. It can't put any more there. Or argon, right? It's not so much what is about these first 2 orbits in this case, like chlorine, for example. We don't care about the first 2 because chlorine can't show that off to anyone, right? Nobody's going to see that in the Instagram photos. You're only seeing the outside shell. So they always want like the maximum that they can get. So they always have a tendency to like get more. So Probably made all that worse for you. So let's talk about now the first case where atoms are not, they're starting to do stuff to each other. Here you have atoms stealing from each other. And you might ask, well, how do I know when one atom is going to steal from another? Don't worry about it now. You'll start learning some of them when you take other science classes. Like, that chlorine is a thief, right? Chlorine steals electrons. That's just what chlorine does. And sodium's a simp. Sodium just gives electrons, and so does other things like potassium, right? So let's look at this. So chlorine, you don't have to know this for like a test, but the atomic number of chlorine is 17. That means 17 protons, 17 neutrons, 17 electrons. So if we add up all these electrons, here's 2, here's another 8 on the second shell, that makes 10. And then the other 7 is out here to make 17. So there's 17 electrons going around it. So it's got 17, but remember, they always want to be more, right? Chlorine's thinking about, I don't have social media. I don't know what the hell a snap's called, but you know what I'm saying, right? So chlorine wants to look good. And so chlorine wants that other electron, even though it has no right to it. So chlorine goes to sodium and says, hey, sodium, you only have 1. So that's kind of lame. And, you're never going to make it. And so chlorine steals it. We call it electron transfer. So chlorine's going to steal the electron from sodium. And so there they are. Sodium's missing an electron, which you would think is negative, right? That's like, that sucks. No, it's like we got to reverse it. Getting something stolen from you or the loss of an electron is positive. And then gaining an electron is negative because stealing's not right. It's like a negative thing. So chlorine has, if we check out chlorine still has 17 protons. Protons don't ever change, right? So 17 protons, which are positive, 17 positives, 18 negatives now, because it stole that other one. So it's got 18 negatives going around it. So the balance has been thrown off. And so chlorine's negative. Same thing with sodium. Sodium lost an electron. So it's got 11 protons, which are positive. It has now only 10 electrons, which are negative. So now it's positive. And here's a screwed up thing. Chlorine's going to turn to sodium and say, hey, you want to go watch some Netflix? And, sodium's an enabler. And so sodium's like, yeah, okay, fine. And they get together. They hook up. And so they're going to stick together now. They're going to bond together. Is it a bond based on love and trust? No. It's a bond based on theft. So if I were to ask you, do you think that sodium and chlorine are going to stay together a long time like Kim and Kanye? I don't know why that just came in my head. No. They're going to break up. So you start to learn about like bonds, like some bonds are tight and they're going to stay together. Obviously, they stay together. Look at your computer. Those are bonds that are being held together. But there's some bonds that don't do as good of a job holding together. So this is called an ionic bond. Let me show you. Oh, wait, here we go. So when something is positively charged, we call it a cation. Anion negatively charged. I remember it that the cation's positively charged because the T makes like a plus. So like the T for cation is like a plus sign. And anion doesn't have a T in it. So I don't know. Whatever, it works for me. Shut up. I have my degree. And I was just giving you examples, right? Because these minerals in your body, Like all the minerals on the side of a cereal box, iron, zinc, whatever, they're all positive or negative. So you need to know cation, anion, because that, you're going to see that after this class. You're going to see those terms. Does anyone have any? Oh, look, you guys are still here. Does anyone have any questions so far? Are we good? I'm going fast, but I'm going to keep blowing through. All right. So, ions. And that's an ionic bond, right? That's table salt. It's sodium chloride. It's sodium and chlorine. There's the positives and the negatives are sticking together. Just like Paula Abdul said it best, opposites attract. 2 steps forward, 1 step back. Full of like useless, because it's hot.
I have a question.
Yeah.
So if atoms are stealing electrons from each other, that's when they become an ionic bond?
Yes.
Okay.
And we call it electron transfer. Remember, they're on Bravo, so they're like rich. They've got money. And when rich people steal stuff, we call it transfer. So they transferred electrons. All right. So that's one type of bond. And the electrons changed in those atoms. So like in sodium, the electrons are different. In the chlorine, the electrons are different, but the protons don't change. Right? So it's still going to be whatever the atomic number is, right? That doesn't change. This is another type of bond, the most common type of bond. So if you see atoms together, so like look at this one, right? These green and yellow represent whatever atoms, chlorine and sodium, but they're telling you here, like you see a positive and a negative, right? But otherwise, if you didn't see that and you didn't know what they were, just assume that they're using this bond, covalent bond. So covalent bonds cohabitate their valence shell, right? Remember, the outer shell is called the valence shell. And so co means like sharing, right? So they're sharing electrons in their valence shell. It's kind of a good way for them to solve their problems and like hook up together. So if you look at hydrogen has 1 electron on that valence shell. Hydrogen only has 1 shell. So that's the outer shell, right? There is only 1 shell, but it's the most outer shell. So we call it the valence shell. So it only has 1 electron, but we could fit, how many electrons could be on that first shell? If you're thinking 2 to yourself, you're correct. If you said 2, you're on mute. So yes, 2. So it's only got 1, but it wants 2, right? It wants to be everything that it thinks that it is. And so sharing electron with another hydrogen can kind of like help that, or sharing an electron with any atom can help that hydrogen get the other one. So like this electron here is going around hydrogen and going around this hydrogen. That's how I picture it in my mind, at least. So it's like figure eighting around each other. That's holding them together. They have an interest in staying together because they're sharing electrons, and they both they're going so fast around them that each one feels like it has 2, even though it technically doesn't. But it's like the effect of having the shell filled up. Same thing with oxygen. Oxygen is sharing. Here, they're not sharing 1 electron. They're going to share 2 electrons. And there's only a few examples when they share 2. But my point is, all right, you know what? Forget this one. Let's look at the water. Oxygen here, oxygen has normally 6 electrons going around this outer shell. But because it's sharing with 2 hydrogens, it looks like it has 8. So it feels like it's complete. snap photo. And same thing with hydrogen. They feel like they're complete because they're getting, the oxygen is sharing one of its electrons with this hydrogen. Oxygen is sharing one of its electrons with that hydrogen. So it's just atoms sharing electrons. In all four of these cases, they're sharing electrons. And I've got rules. There's some rules about it. You can fill your shell, but that's it. You can't get any more in there. See, so like hydrogen, no other atom can share with hydrogen at this point for two reasons. One, hydrogen's filled up. Two, hydrogen has nothing to share. So that's not how sharing works, where I just give you something and you give me nothing. So you can't, once you fill the shell, it's done, right? You share one or you share two, you get two. You share what you get. You don't share, like I give you 2 electrons, you give me 1 electron. It doesn't work like that. Whatever you share, like whatever you give, that's what you get. And I want you to know how many bonds man, I'm getting myself. I shouldn't be like in here breathing this air. And you need to know this right here. How many covalent bonds can these 4 make? So if I go back to this here, you notice that hydrogen is always making 1. See, here's hydrogen. It's only attached to 1 carbon. This hydrogen is attached to the same carbon, but they're only attached to 1 thing. There's nothing on the other side of hydrogen here. Oxygen will make 2 bonds. So look at these 2 oxygens here. Let's look at this bottom one first. It's made 2 bonds. It's made one with 1 hydrogen, and the other is with another hydrogen. So it has 2 electrons to share. Right? In this case, it's sharing 1 with this hydrogen, 1 with that one. Here, it's taking both of its electrons and sharing it with the other oxygen. So you imagine oxygen is having 2 arms, right? So I can take each arm and grab onto something, or I can take both my arms and grab on to another oxygen. It's like a middle school slow dance, just like that. I'm not letting you go. It's probably not like that nowadays. And carbon, if you look down to carbon, carbon always makes 4 bonds. So imagine carbon is having 4 arms, right? So that's what it's doing here. It's taking each one of its arms is grabbing onto a hydrogen. So the only thing that you really need to know is like these bonds. Like you don't have to know, well, why is carbon grabbing onto hydrogen here, and why is oxygen grabbing onto hydrogen? Like why are these existing? You don't have to know why they're happening. You just look at it and say, okay, well, carbon, and look, see these like dashes coming out of it? That's the same thing as this. Carbon's got 4 dashes coming out of it. And hydrogen only has 1 dash coming out. Oxygen always has 2 dashes coming out, right? Nitrogen would have 3. So if I were to put a nitrogen, let's say if I were to take this oxygen away and put nitrogen, can I leave it like that? Nitrogen with 2 hydrogens? Does it make sense to you? I hope you're shaking your head no. You're not shaking your head, but I hope you're thinking in your head no. That means you're paying attention. No, you need 3. So I would have to have a 3rd hydrogen out here or something. It's got to be a 3rd atom, right? So nitrogen always bonds with 3. Oxygen, 2. Hydrogen, 1. Carbon, 4. That's why I called carbon our star player, our leader, whatever I called carbon. It's like the best one. All right, so biology is a study of things that are organic. So you have like organic and inorganic. Organic is anything with carbon. So everything that we study is carbon-based. Things that are living are carbon-based. All of your food, carbon-based. So things with carbon, we call it organic. So it's a different meaning than like at Whole Foods, right? Um, Himalayan salt, is it organic or inorganic? Inorganic. No carbon. Water, glacier water, inorganic. No carbon. Water's just H2O. Carbon monoxide,
Organic.
organic. Delicious carbon monoxide. Diamonds, organic. Of course, your food. Anything that was living, anything that was once living, like oil, like gasoline, dead dinosaurs. Dinosaurs were living. So that's it. It's organic. Yeah, I'm saying there are double bonds and triple bonds. I showed you one example here of oxygen with oxygen. The only time you're going to see a double covalent bond where they're sharing 2 electrons is oxygen with oxygen, carbon with carbon. So sometimes one carbon will take 2 of its bonds and grab onto another carbon. And sometimes a carbon and an oxygen will do it together. They'll take 2 of their bonds and grab onto each other. That's the only times you're going to see it in this class. It's always going to be an equal sign, and then you know what the equal sign means, right? Usually 90% of the time you're going to see these dashes, right? And that just means they're sharing 1 electron. Here they're sharing 2. Okay, so any questions on covalent bonds? That's the main kind of bond you're going to come across. Fucking COVID, man. I wish I could, like right now, I could be doing this class from like a cafe or something with like AC blasting on me. All right, so we've talked about 2 bonds. Ionic, it's a positive and a negative. It's like 2 magnets sticking together, right? Covalent, they're sharing. So it's not a positive and a negative. They're sharing electrons. There's actually 2 bonds going on here. This is a molecule of water. I first want to talk about the covalent bond there that we're looking at. So you guys can see this, right? Okay. I'm sure you would have told me by now. So where this arrow is, this blue arrow, this is a covalent bond between this hydrogen and this oxygen. Same thing here. Between this hydrogen and this oxygen, that's a covalent bond. This is a little bit of a different type of covalent bond. Usually covalent bonds, they share nice and equal. I give my electron to you, you give your electron to me, then we'll swap back, and we'll share, and we'll be happy. So that's normal. That's almost every type of covalent bond. They're sharing nice and equal. Some bonds, especially hydrogen and oxygen, they don't share equally. Oxygen doesn't play fair. Oxygen's like that friend that you go over to his house and like he never gives you the controller, right? He never lets you play. But when he's at your house, he's got your controller, insists on single player. He's a douche. That's oxygen. See, oxygen oxygen's really a douche, and people think that oxygen's really nice. So if you ever heard of like antioxidants, that's against oxidants, like against oxygen, because when you piss off oxygen, they can do a lot of damage in your body. But anyway, here it is with water. It's hogging the electrons. So the electrons going around hydrogen, and then it's going around oxygen. Then oxygen wants to take it again. Oxygen wants to take it again and again and again. And you get my point. And then oxygen will give it back to hydrogen. So it didn't steal the electron. Oxygen's not stealing it. It's just got it all the time. Like almost all the time. And then look, oxygen's not happy doing that to one hydrogen. In this case, it's doing it to another hydrogen. Right? So it's working two hydrogens. It's taking their electrons most of the time. So instead of a 50-50 sharing situation, you've got like, I don't know, I'm making this up, but like 90-10. So what happens is that whenever you go to check out hydrogen, you see the hydrogen doesn't have the electron most of the time. So that doesn't make it a full positive. It makes it a partial positive, right? It didn't lose its electron. The electron wasn't transferred or stolen. It's just being borrowed extensively. And so this little delta D, it's like a Greek D. This means partial. So you have a partial positive on that one end. And then the oxygen, it's always got like these extra electrons from the hydrogens. You know, not, it didn't steal it, but it's always has it. And so you've got like a negative little pull on this side. So it's like, it's not like a magnet where you have like a full positive and a full negative, but you've got these pulls. So on one end of water, you've got a negative pull, and the other end, you got a positive pull, or like partial charge. And so we call this a polar covalent bond. This right here. Between the hydrogen and the oxygen, it's polar. All these bonds, with the exception of this one, but these other three, non-polar, which means to me regular, a regular, happy, normal covalent bond. Non-polar, all this is non-polar. This is non-polar. This is non-polar. This is polar right here. Right here and right here. You see oxygen won't do that with itself, with another oxygen, right? It has respect for other oxygens. It wouldn't pull that on carbon. Yeah.
Is oxygen only doing that to hydrogen?
Yeah, for now. I mean, there's like if you take chemistry, there's some other examples of polar covalent bonds, but for us, just hydrogen. It picks on hydrogen. Oxygen needs to read up on B best. That's my opinion. All right, so yeah, so polar covalent bond. So with water, or anytime you see an oxygen and a hydrogen, anytime you see it, you assume that it's a polar covalent bond. You see an O and an H, oxygen and hydrogen, and you know they're not sharing their electrons equally. And you know the hydrogen's the one that's getting screwed over. But that causes something. So they're not sharing equally, right? So you've got like a positive pull here, and you've got a negative pull here. So this is a water molecule. Here's another water molecule. You already see what's happening here. So you got that positive pull here. You've got a negative pull here. It's kind of like an ionic bond, but it's only like it's not as strong as ionic bond, right? It's not a positive and a negative sticking together. It's like so like if it were an ionic bond, it would go like this. And so if I take this coffee cup and I pull it, my phone comes with it, or vice versa, right? Little bonus coffee. But a hydrogen bond works a little bit different. They're not like touching like magnets. They're like this, right? And so if I take the coffee cup and I kind of pull it, this is going to come with it. Or if I take the phone and I pull on the coffee cup is going to follow it. If I take the phone and I jerk it away, it's just going to break away. right? But that wouldn't be like that with an ionic bond. If I take the phone and I jerk it, the coffee cup's coming with me. What a stupid example. I hope you get what I'm saying, right? So they're kind of attracted to each other. This water molecule is attracted to this one. It's attracted to this one. That holds all these water molecules together. Those are hydrogen bonds. So you've actually got two kinds of bonds going on here. This dash right here is called covalent. Polar covalent, though, because it's a hydrogen and an oxygen. So we're going to call it a polar covalent. So polar covalent, between every red circle and white circle is a polar covalent. But you also have hydrogen bonds in between one water molecule and another water molecule. So covalent is strong. Ionic is not as strong, because remember, that's a relationship based on theft. This is even weaker. So the hydrogen bond's really weak. If I heat this up a little bit, if I heat up water, what happens to water? It becomes steam, water vapor, steam. Is steam still water? It is, right? It's still water. You didn't destroy the water. You didn't heat up the water so much that the hydrogens and the oxygens all broke apart. Like, they're not sharing equally, but they're still sharing here. What you broke apart when you heat up water is the hydrogen bonds. So this water molecule goes away that way, and this water molecule goes that way, and so hydrogen bonds are pretty easy to break apart. Heat, a high heat will do it. If you change the acidity, that will do it, and we'll talk about that in a minute. So anyway, we've got three bonds that we've discussed. Covalent, and under covalent, there's polar and nonpolar. And that just, what's the difference between polar and nonpolar? Polar does not share equally. Nonpolar shares equally. That's the difference. So we have covalent, ionic, and hydrogen bond. When you have a hydrogen bond, there's going to be a polar covalent bond. I know that's a little confusing, but questions up to this point? It's going to go faster, trust me, because I know we're already an hour. I think I can do this in about 15 or 20 minutes, right? And then that's going to cover everything that's on the quiz. And then if, I don't know if you guys want me to jump into the next one, I can today, or I could just not. Actually, I prefer not to. I don't want to put other information in your head until everyone's taken the quiz. So, but it's up to you. Trees. I put stuff up here to remind me of stuff. Water. Let's talk about water. Water is a very unique substance as far as liquids go. It has unique properties. Obviously, you know, we're all made of water, and our food's made of mostly water, and the earth is made of mostly water, and all that stuff. So what is it about water? Like, why are we mostly made of water, and why are we not based on some other kind of, why aren't we based on oil? Why aren't we oil-based? Because water has some unique properties, and one property is that it's cohesive. So cohesive means it sticks together. Water tends to stick together. If I take one of these water molecules, like I'm pointing to the screen, look at that. Amazing. What an idiot. So this water here, if I were to pull it up, these molecules here are going to follow. Right? So when you pull one water, the other one is going to follow it, and the other one will follow it. So if you look at this like tree, if I grab the water at the leaf and I pull it out of the leaf, all the molecules, it's like a train of water molecules. They're following all the way down, all the way to the roots. So that's an example of cohesion. Water sticks together.
Is that because of those polar covalent bonds?
Close. The other ones. Hydrogen. It's because of the hydrogen bonds that
Okay.
they're following each other. It's a weak bond. It's not very strong, but it's still a bond. They're still attracted to each other. So when one of the molecules evaporates from this leaf, it pulls all the other ones up all the way down the trunk, and it pulls the water from the soil. So like a cypress tree, they're really good at this. Like a cypress tree could suck like 250 gallons of water up out of the ground a day. They're really good at that. They just let the water go from the leaves, and it pulls all the water up. They call that transevaporation. And that's because water sticks together. If you take a paper towel and you put it up to like a spill, just the corner of the paper towel, that'll get all the water up. You just watch it. It'll soak up it. As long as the paper towel's dry, the water keeps soaking up into the dry part of the paper towel, and it sucks all the water. You see the water following the other molecules. So it's cohesive. It has a high surface tension. If any of you have belly flopped into a swimming pool, then you know. It can act like a hard surface. Right, so these water striders, they take advantage of that. So for a brief second, it acts like a hard surface. Why do we care for us? I'll give you an example, like a practical example, like our lungs. Our lungs have to be moist, but the oxygen has to get from the lungs into the blood. So it's got to break past that water barrier, right? And so for us, we're okay. We make this chemical that it's called surfactant. We make a chemical that, what, my phone's blowing up. The other faculty, do you hear all my little dings? This is faculty when they should be working. All right. Nobody's going to watch the recording, so I'm fine. Yeah, so the lungs, right? You make this thing called surfactant, and it lowers the surface tension. If I were to put this chemical surfactant in here right now, this water strider would sink right into the water, right? It lowers the surface tension so that you can get the oxygen past the lungs and into the blood on the other side. That's why, like, that's the issue with premature babies, right? That's it right there. It's one chemical. They're not making surfactant. And so when they breathe in, because the lungs are like one of the last things to develop in babies. So when they breathe in, the oxygen can't bust through the water in their lungs and get into the blood. So that's why you got to hold on to them until they can start making their own surfactant and the oxygen can get into their blood. So water has a high surface tension compared to other liquids. Andre Agassi. I should just leave that and move on. All right. What do I want to say? It cools as it evaporates. You would say that's not really a big deal all the time. Maybe now, like I'm sweating like crazy right now. But on a day in the end of November, when I'm just in a classroom that's cold, you're still sweating. You just don't realize it. You're making sweat every day of your life. You don't realize it. And the other thing you don't realize is how much of a difference it makes. If you stop sweating, you're dead. Like today, if you stop sweating, you're dead. You're gonna overheat, right? We don't realize, when it's like super hot, we think it's like, okay, I'm sweating, but it's a life and death thing. It makes that much of a difference, right? So water evaporates. As it evaporates, it cools surfaces. That makes it different from other chemicals. So high surface tension, cools as it evaporates, cohesive, expands as it freezes. A lot of other Liquids don't do that. Alcohol doesn't do that. Keep a bottle of alcohol in your freezer. You shouldn't have any alcohol, but I'm just saying. You put a bottle of alcohol in your freezer, nothing's going to happen. Put a bottle of Sprite in your freezer, it's going to explode. Water is a universal solvent. So at this point, I'm explaining some terms here, which you have to know, because this word solute, for example, will come back in anatomy and physiology, for example. Right, so salt is a solute in your body. Water follows it around. And so if you can get rid of that solute, if you can get rid of salt, the water is going to follow it. So the solvent, which is water in your body, follows the solute, which is salt. I think the Kool-Aid's an easier example. The powder is a solute, and the water is a solvent, and the refreshing Kool-Aid is the solution, the Kool-Aid that you drink. But we're missing a part of the Kool-Aid, huh? You can't just put the powder in the water. That wouldn't taste good at all. You also need sugar. Sugar is another solute, right? It's the thing that's going to dissolve. The thing that does the dissolving is called a solvent. So, and I gave you some examples. Water is not the only solvent. You have alcohol. So I give you an example of like NyQuil or whatever. And nail polish, right? Acetone. Because acetone evaporates super fast. You can't make nail polish with water, right? You put it on your nails and it's going to stay forever. But the acetone, it evaporates really quick. It has a low evaporation point compared to water.
And I had a couple of connectivity issues a second ago, but I had the high surface tension expands as it freezes, and then what was the one, I guess, before that the water expands as it freezes, as far as like the properties of water go? The property before that, I think it was something with water's evaporation.
It cools surfaces as it evaporates.
Okay. Yeah. Now I get why you're talking about sweat. Okay.
Yeah. What I don't understand is like what this dude is doing on here, because tennis has moved way beyond that. That's like the 80s or something. All right. He used to have long, luscious hair for you old people that, anyway.
So like if you're cooking and you add salt to like, I don't know, boiling like water or something, the salt would be the solute, or
yeah, the
and
salt.
then,
The salt is the solute.
okay, and then like the water, like whatever it is, whatever liquid is in the pot would be the solvent, right?
Yeah, and then
Okay.
what happens when the salt melts? Now, what's the salt water?
The solution.
Yeah.
Okay.
So water is a universal solvent. It's like great for dissolving things. It's great for holding other things. It's like the best one out of all the liquids. Not that other liquids can't be solvents, they are, but water's like a great one. It makes it different from other liquids. Okay. Let me talk about this, even though I don't like this photo now. But the other part of this chapter on water is acids and bases. And so here, let's take this molecule of water right here. Right? So my first question to you, and you could just answer to yourself if you want, is what kind of bond is going on between this hydrogen and this oxygen here? So covalent, you're right. What kind of covalent?
Polar.
Polar. And what does a polar covalent mean? Like, what are they doing?
Oxygen's being a douche. And
yeah, oxygen's being a douche.
Taking more of the electrons, or
yeah,
using
unequal
so
sharing.
frequently.
They're unequal sharing. Right, correct. So Oxygen's doing it with this hydrogen. Oxygen's doing it with this hydrogen. Sometimes that's just a lot of pressure on these hydrogens. Like it's getting, how long is hydrogen going to be treated like a punk? And so hydrogen sometimes will just be like, look, I'm out. I'm gone. I'm leaving this sick triangle that we have going on here. And that's it. Bye. And of course, it leaves without its electron because oxygen's got it. But hydrogen doesn't care. You know what? Keep your electron. I don't need it. And so hydrogen leaves. And so what happens when hydrogen goes away without its electron? What does it become? The hydrogen ion, it becomes a cation, right? It becomes H plus because it doesn't have the electron. So and really hydrogen, all hydrogen is, it's an electron and a proton. So it's one proton and an electron going around. Hydrogen's kind of different than all the other atoms because hydrogens don't have neutrons. So hydrogen, all it is a proton and an electron. So if you take the electron away from hydrogen, it's only a proton. That's it. So we call those, and it's not on here, but we call those protons. H plus is a proton. The more protons you put in something, the more acidic it becomes. So the more protons you add to a solution, the more acidic it is. So if you look at what happens, this hydrogen gets sick of being in this relationship. It leaves without its electron. On this side, you've got the O and the H left over. Look, here it is right here. There's the O and H. That's this O and H. The other hydrogen is going to hang out. No, I'm with you. I'm with you, douchey oxygen. Don't worry, I'm going to stay with you. And then there's an extra electron. So that's why we put over here, we call this a hydroxide. So forget about this. If this hydrogen leaves without its electron, this thing right here becomes a hydroxide ion. So that's kind of what can happen with water sometimes. Sometimes one of the hydrogens gets pissed off and takes off without its electron. That can make things acidic. This hydroxide ion can make things basic. See, here it is right here. Like, where's the other hydrogen? It took off. Now there's an extra electron in this, and the other hydrogen's still here, so we call it OH minus hydroxide. And so it depends on, so for pH, the more protons, and so that's why I put this H plus. You can call it a hydrogen ion. A proton maybe is a better word. The more protons in a solution, the more acidic the solution is. The more hydroxide ions, that's this OH negative. And you're like, well, why is it negative with the H and not with the O? It is with the O. Just, I don't know. It's how they draw it in chemistry. So you're looking at it as one molecule. So the more hydroxide ions in a solution, the more basic it is. And look at the scale. This is the pH scale. I'm not going to make you memorize all of this. It's just to give you, and it's telling you here, things that are lower numbers are more acidic. As I go from 7 to 6 to 5 to 4, it becomes more acidic. As I go from 4 to 3 to 2 to 1, it's more hydrogen ions, more protons. The concentration of protons becomes greater as I get to a lower number. And as I move to a higher number, it becomes more basic and it becomes more hydroxide ions. One of the other things is that people think, oh, acids are bad and bases are good. No. Look at this base down here, oven cleaner. That'll burn the shit out of you. Try breathing that in. I did once. I'm stupid, I didn't know. It really burns. Or if you watch Fight Club, right? The lye that they pour in the hand, that's over here around 13, 14, right? So you're going from extremes. You don't want, when you move further away from 7, 7's neutral. So as you move further away from 7, it becomes more caustic. Right, so these are just some examples: bleach, ammonia, like actual ammonia, not like the household ammonia. We used to use those in EMS. We used to use them as, to wake people up. They banned them like probably 2 years ago because they're sticking them up people's noses. But yeah, it works. It works, man. If you ever smell that stuff before, it'll wake you up. You're not going to sleep through it. Even if you're passed out drunk, you're going to get up. Right? It's all right. So anyway, these are some ideas. So remember, under 7 is going to be a base. I mean, an acid. And over 7 is going to be a base. I think I have a question about that on the quiz. So just remember, under 7 tends to be acidic. And don't forget this, it's times 10. Right? So it's not that like 5 is a little bit less, or is a little bit more acidic than 6. Right? No, 5 is 10 times more acidic than 6. And 4 is like 100 times more acidic than 6. It's times 10 each time. So like if I'm going with like pure water and I want to look at tomato juice, so 10, 100, tomato juice is like 1,000 times more acidic than pure water. Coca-Cola is what, 10,000 times more acidic. So yeah. So you see sometimes people, they like chronic Diet Coke drinkers. And, there's people that drink like a 12-pack a day of this stuff, right? And it rots their teeth out. And, studies show that your body thinks it's sugar. So you might as well be drinking the regular stuff because it's I mean, it's not exactly true, but I mean, your body's treating it like sugar, and it's taking in, it's putting fat into the cells anyway. So I mean, diet drinks, you can't have something that tastes sweet. You can't get something for nothing. There's no like shortcuts with food. It's not going to taste good. That means it's good for you. All right. Was that my last slide? Oh, that was my last slide. So, any questions?
Can we revisit slide 19? I don't really feel like I was getting that one.
You don't have to get it.
Okay.
If I were to redo this slide myself, I would take these 3 things out right here. So take this water away.
Okay.
I would have this one hydrogen here with the plus sign by it. That's how I would do it. And I would call that a proton. This one little hydrogen with the plus sign, I'd call it a proton. I'd get rid of all this. And then on the other side, I'd have this hydroxide ion.
Okay,
I should have taken it out, this whole photo.
So basically the very first little, I guess, hydrogen oxygen bond, is that a hydrogen bond that we're looking at?
Here?
Yeah. Like, and then with the 3 little.
Between this water and this water?
Yes, sorry.
Yeah. These and these 3 dots are the dead giveaway. Like 3 or 4
Right.
dots. That's always going to be that's always the sign that it's a hydrogen bond. I forgot to tell you guys that.
Okay. And so you were saying that hydrogen then leaves the water molecule?
Yeah.
But it doesn't take its electron with it, right?
Correct.
So it becomes
this
like,
one's showing you something else, which is also something that I didn't want to teach it to you guys. So this hydrogen did is that it left and it went on here.
Okay.
But I'm not but really what I'm trying to show you is that water can become both protons on one side or a hydroxide ions on the other side.
Okay.
In this case, because this, you look at this hydrogen here, it comes over and it sticks right here. So that's no longer a proton just floating around in the solution. It's stuck to something else. So we don't even count.
Okay.
And then now what you have is, so in this example on this slide, you only have the hydroxide ions. So this.
Okay, I get it now. I was looking at each one as like a separate sort of thing, and I get it now.
Yeah, I was explaining it really in a bad way. But I think the video might be a little bit better. I hope.
Okay, I don't think I have access to any of that yet because my classes are weird.
Oh, okay. Are you the one that
Yeah,
getting dropped off?
yeah, I'm still trying to get in class.
I gotta call somebody today. I'm gonna talk to the registrar like after our class and
Okay.
see, like what's up.
Okay, thank you.
I'll let you know. Any other questions? I am inclined to stop here and not jump into the new stuff because I don't want to, like, sometimes people focus on just the new stuff and then you're going to take the quiz. It's not going to be on there. You know, like you spend most of your time studying stuff that's not going to be on the quiz. I don't know what's up for. I think Monday I think I'm going to go into the classroom and stream it, and you can watch it just like you're watching. As far as the quiz, I am using Proctorio, so you're going to need to download Google Chrome, and then actually, can you guys see my? Hold on, let me try to open it. Since I'm still sharing my screen. Oh, because it's already open. I can't open. Can you guys see that, like my new tab and stuff? If you look up here, these are all my extensions. I think it's just like this shield. Yeah, see how it says Secure Exam Proctor? So that's how I know it's there. You're going to want to see that shield before you take the test. It's recording you. You know, the main thing that I don't want you to do is I don't want you to like have your notes and just like do this. Like, I don't know if you can see what I'm doing with my head, but like you're very obviously looking at like notes. So I would like for you to not do that. And don't do this. Keep looking down. You're very obviously looking down at your phone. Like I'm not going to know. Everybody knows. You're like, so yeah, just it's not hard. It's 10 questions, multiple choice. So no, you can't have all the answers in front of you. You won't be able to go to new tabs or anything like that. You could talk to yourself. Some of you have taken it, spent the whole test talking to yourself. You're like this, reading the question, talking. Man, I don't know. What is that? What is that? And like looking off to the side like this. Man, what is that? That's all right. You don't have to like keep your face like on the camera. That's going to be weird. I could tell the difference between like looking at notes and just like, man, like talking to yourself, talking your way through it, like looking around and stuff. That's okay. Right. So don't freak out. I don't want you to like look at notes, and I know what it looks like. All right, so let me stop recording. If you guys don't have